Hello student, this is Mr. Teo. Last lecture we talked about the 7 rules of block diagram manipulation, and we went through several tutorial questions on how to do the block diagram manipulation of some of the blocks. Now today we're going to continue with block diagram manipulation, but at the same time looking at superposition theorems. And so without further ado, I will start the lecture notes and then we shall discuss along the way.
For this week we will start off with example 1 of block diagram using superposition theory for linear system. For this example, the system output Z is linearly and independently affected by inputs X and Y. As such, we can use superposition to solve for expression of Z just by considering the effect of Z due to X and Y separately.
Now, this question is also related to block diagram manipulation, but it doesn't look very complicated. But when you actually solve it, it is slightly more complicated than it looks, right? Now, what happens is, of course, the question describe it as a linear system, so that you can use superposition, meaning that the output is affected by the input independently, meaning that Z is affected by Y. But at the same time, it is also independently affected by X. So X has some components. So if you sum the effect of Y on Z and then effect of X on Z, they can be summed directly. So therefore, we can use superposition theorem. Now, the first step of using superposition theorem, of course, we set Y equals 0 and consider only the path for X. And that's exactly the first step we're going to do.
Step 1. We look at the effect of output Z prime by X. We set Y equals 0, then simplify the block using the rules learned in the last lesson.
So basically, as we say that we want to look at the effect of X alone, so we set Y equals 0. So you realize that the Y is being removed. And because Y is being removed, so this summing node is no longer valid. So actually, we can also remove this node and then put through the whole thing, right? Therefore, the output that is affected, we call it Z prime. We don't call it Z anymore because this is not actually Z, it's just portion of Z. So we call it Z prime, right? So
Step 2. Since the summing node between G1 and G2 is not summing with Y, as Y is set to 0, we can remove the summing node.
Okay, so this part, the summing node I have already mentioned, so we will proceed to the next step.
In step 3, we multiply G1 and G2 together to get G1, G2, using rule 7 for negative feedback loop.
So basically, just now you have G1, G2 with the summing node in between removed, so you can combine them together by multiplying G1, G2 together. So with that, you have a forward gain and a feedback gain. So they basically just form a negative feedback loop, right, with minus here. So it's basically you can use the rule 7 to simplify this G over 1 plus GH, right?
We can simplify from step 3 to step 4 just by applying the G over 1 plus GH.
So after applying the G over 1 plus GH, your G is G1, G2, then your H is H itself. So basically G1, G2 over 1 plus G1, G2, H. So that is basically applying step 7, right? So therefore you can write in this sense Z prime, actually Z prime over X is this expression. So Z prime is essentially this expression multiplied by X, right? So X multiplied by this expression give you Z prime. So
now for part B, which is step 5. We want to consider the effect on Z prime due to Y. Hence now we set X equals 0.
Now for this second portion, we want to look at the effect of Z due to Y. Now no more the effect of X. So basically we kill the source for X and then remove it from here. But of course the summing node, we still have not removed it. And then we consider the effect due to Y. And then we call this Z prime instead of Z or Z prime. Right? So it's Z double prime here.
Moving from step 5 to step 6. We can remove the summing node since x is already set to 0. One thing to take care is since h is a negative input to the summing node, we must insert the minus sign to h block when removing the summing block.
So basically, we try to remove the summing node, but because this is a negative feedback, so there's a negative sign involved. So we cannot just remove it. Basically, we got to add the sign in first before removing it, so that it still has a negative feedback to this G1 itself, right?
In step 7, we combine G1 and negative h by multiplying them together. Step 7 also look like a positive feedback, using rule 8.
So basically, if you combine the feedback factor h, minus h and G1, you can combine them by multiplying together, of course, including the negative sign. So now your forward path is G2, but your feedback path is minus G1h, right? So again, this form a positive feedback loop, and of course, positive feedback loop in your block diagram manipulation is rule 8, right? So you can use rule 8 to further simplify this. So it's actually G over 1 minus GH, right? So
we can simplify from step 7 to step 8 using G over 1 minus GH. Note that denominator is 1 plus, not 1 minus, because minus sign multiply with minus G1H becomes plus.
So take note that actually it is a minus, but because the H portion, which is constitute of minus G1H, actually multiplied by the minus become plus G1, G2H. So therefore, that is the final expression for Y and the effect of Z prime prime. So right now, similarly for the first case, you have Z prime prime equals to this guy times by Y. So that is Z prime prime. So we now have Z prime and Z prime prime. So Z is none but adding Z prime and Z prime prime together.
Finally, we add Z prime and Z prime prime to get Z.
So basically, the Z expression will be the effect due to X and the effect due to Y. So that's how you get the expression for Z for using superposition theorem. So this is quite straightforward. Let's look at further example. This is just example 1.
For this example 2, we want to simplify this more complicated block diagram into one block. We want to unentangle many loops overlapping loop. First move is to move the summing node to the back of G4 as indicated by the arrow. Here we apply rule 2 to make the move.
Now this is this example is a bit similar to the question number 7-3, number 7 part 3 in your tutorial 3, if I'm not wrong, tutorial 3 or tutorial 4. So basically, okay, the first step that is taken here to simplify the crossover of all loop is to bring the summing point here. But in order to bring the summing point here to the back of the G4, because the signal is flowing from here down towards the output, right? Rightfully, at first, when it goes down here, it just sum and then go out. It don't go through G4. Now, if you move it ahead, then it will go through G4, then go to the output. So therefore, you have additional G4. So here, you must insert a 1 over G4.
Remember, when we move summing node to the back of G4, we need to insert 1 over G4 to the path of G5. If we counter-check by writing the expression of E3 is the same before and after the move.
So basically, as what I've said, you need to insert 1 over G4. Now with this here, you can realize that G4 multiplied by G6 can be combined, right? And then also another thing is you can swap the summing node, because of swapping of summing node, there's no consequences and no change. So basically, 2 steps can evolve in the next slide. Swapping of the summing node and then combining of these two. And these two also can combine, because G5 times by 1 over G4 becomes G5 over G4, right?
Next, we can combine G5 and 1 over G4. Similarly, we can also combine G4 and G6. To further unentangle the loop, we apply rule 3 to swap the summing nodes.
So basically, you combine these two and you swap this guy, and it's a negative, is a positive feedback loop, right? And then this guy is a feed-forward loop. This guy is in a feed-forward loop. So basically, there's a lot of other things that you can combine.
For G4, G6 and H1, we can use Rule 8 for positive feedback loop. In this case, G is G4, G6 and H is H1. For G3 and G5 over G4, we can use Rule 6 for summing point in front of G
right?
blocks.
So these are the two rules that you can do. So this one you use G over 1 minus GH, right? So for this guy, it's just simply summing this with this. So it's G5 over G4 plus by G3. So there's new block to be simplified. Of course, G1 and G2 you also can combine.
For G1 and G2, we just combine them to G1, G2.
Right. So basically, you get these three combined together, and then basically you can multiply all of them together, and that form your new G here. That form your new G, and then your H is here. So there's again yet another negative feedback loop with this combined G and this H2.
For the three block in series for the forward path, we combine them by multiplying them together.
So with this this thing, you actually can solve your G over 1 plus GH using this as the gain G and this as the feedback gain H, right?
Again, we see a negative feedback loop. Hence, we can apply Rule 7 to simplify it further. The right-hand side show the algebra involved in the simplification.
Here it is the, no, where's my cursor? Now here it is the G over 1 plus G H, right? Because it is negative sign, therefore it's a plus. Then after that, you make this 1 the same denominator, so all of them have the same denominator, right? So with the same denominator, you can combine them together as this, the top plus by this side. So this same denominator cancel each other, you are left with the numerator, right? Numerator of the top and the bottom, right? So with this new numerator, you basically can slightly further simplify by multiplying in the 1 over G4 and 1 over G4 here. So that makes up this final expression over here. So it's not really difficult to manipulate. You just get to be more careful. But sometimes error do happens because we are still human, right?
Finally, after simplification, we get the final expression within the block.
So basically, for such kind of block diagram manipulation, is a lot on practicing. So practice makes perfect. So the more you practice, the less mistake you can have, and therefore you can solve it very accurately, right?
For a plant that is classified as first-order plant, in its time domain equation, it contains the first derivative expression. When converted into the S domain, it will appear as K over tal S plus 1. The highest power for S in the denominator is 1. Hence, this is a first-order system. Notice that K is the steady-state gain. Tal is the time constant. On the graph, tal can be estimated from time 0 to when the graph reaches 63% of the final value. Settling time is 5 times the time constant where the graph reaches close to the final value.
Now, this is, of course, the start of introducing everyone to the first order system, and then, of course, subsequently to the second order system. Now, we will not go beyond second order because as it go beyond second order to third order, fourth order, the whole expression and analysis will get very complicated. And as our poly level, we will stop at second level because it is too complicated to solve. Right? Maybe in your university degree, if you ever go up there and then if the professor wants you to solve third order, fourth order, that it may not be surprising to me. But as for now, in the poly level, we will just go for first level and second level. But as you have guessed, first order will be the simpler form of the two. So first order is simpler than the second order. So first order, the general equation will look something like that with K over tau S plus 1. Now, K is your final steady state value, right? Steady states. Now, I always like to discuss steady as waiting for a very long time. So take, for example, if you are a guy or a girl, you want to find a boyfriend or girlfriend, a steady. So you must wait for a very long time to see how this person behave. So time is the testing factor, right? So So the key is, if you want steady, then you have to wait for a very long time. Now, likewise, for electronics, you want to see whether these values stabilize at a certain condition, you got to wait for a certain amount of time. And this basically is called steady states, right? Steady states have occurred. So it's stabilized there. So this is a steady state gain. And of course, for the first order system, if your input is injecting a step function, here we simulated using the step function. Basically, we ramp up this very steep step at time 0 and then goes to 1, and we see what's the response of the output. So for the first order system, the response will follow this particular curve, this slightly purplish curve up, right? So at the point when the values of this curve reach to 63%, we say that this is one-time constant, right? 63% of its final value. So we say that this is one-time constant. We measure down, and the time from 0 to, say, this time constant is 1/8. We call this tau, and tau is basically the time constant, and it is also reflected in your generic equation as tau s, right, +1. So basically, how you determine whether a transfer function is a first order transfer function, we always look at the denominator of the transfer function. Usually in any control, the denominator is more important than the numerator. So basically, we always look at the denominator, we look at the highest power, and for this case, the highest power is s, and therefore we say that s is s to the power 1, so this is a first order system, right? So last but not least, the settling time is basically 5 times of tau. So usually it takes about 5 times of tau to reach about 99.9% of its finest value. So we say that, okay, this is good enough, close to the final value. So we say settling time is about 5 tau. But of course, if you want to reach 100%, maybe it's a little bit impossible, because depending on the gain that you set, it could or could not reach that value. So basically, the rule of thumb is always we use 5 tau. Right? So if you encounter any first order system, they ask you for settling time, you just multiply the time constant by 5, you will get the settling time. Okay?
For a plant that is classified as second order plant, in its time domain equation, it contains the second derivative expression. When converted into the S domain, it will appear as k omega n square over s square plus 2 zeta omega ns plus omega n square. The highest power for the denominator is 2, hence this is the second order system. Notice that k is the steady state gain, zeta is the damping ratio of the system, and omega n is the undamped natural frequency of the system.
Now, this is a second order transfer function, or rather second order system in its time domain. Of course, in the time domain, it has a second derivative. As compared to the first order, it has only first derivative. But the second order, you have d squared y dt squared, right? So this is a second order derivative. So in the time domain, it looks pretty complicated because it's a differentiation, right? But if you do a Laplace transform into the Laplace domain, and basically you can get it into s squared s, and then without s term. So basically, it's a second order because the highest power is s squared, right? Now, the general equation of second order generic equation is basically given by k omega n squared over s squared plus 2 zeta omega n s plus omega n squared. Now, this zeta, it looks something like a y, and in some of the pages we use a snake. So basically, the symbol is not easy to find. So in the earlier day, we used this y symbol, but lately I have been trying to find the more accurate symbol to use it as a snake. So sometimes you see this symbol, or sometimes you look at the snake-like symbol. Basically, it's all referring to zeta. It's just that I have not fully replaced it right now, right? So basically, so your second order system is basically make up of k, zeta, and omega n. So k is your steady state gain, which is also the same as the first order. It is the gain whereby it stabilizes after waiting for a period of time. And then damping ratio. Damping ratio is like the brake you perform onto a system. Now, a system in a negative feedback loop, it has a oscillation possibility. If you configure it into the correct mode, it will start to oscillate. And when it oscillates, this is what we call the undamped natural frequency. That means there's no damping involved. Damping is like a brake to the oscillation, right? So basically, this damping ratio determines how much damping the feedback loop gets. So if the damping ratio is big enough, the oscillation basically will dies away and it stays settled at the steady state. But if the damping ratio is 0, basically you have a full swing of oscillation. So basically, omega n, the undamped natural frequencies, means that the undamped means that omega zeta is equals to 0. So you can see that this zeta here we use Y light. This is we use a snake light. So another page I may use another one because that is because we cannot find a real symbol. But only until lately I found a better symbol to represent it. But because all these are written early in the earlier days, so I still keep it, right? So please don't get confused for the zeta. Now, so in that sense, the zeta is equals to 0, right? The zeta is both of them are referring to the same thing, the zeta. So it's a curly shape, right? So of course zeta can exist equal to 0, can exist between 0 to 1 or equals to 1 or greater than 1. So later we will discuss the impact of different zeta. What does it means to the system, right? So that's second.
Please watch the tutorial late.
This week is the lecture is pretty short, so we will basically discuss 3 questions, which is question 8, 4, and 5. So 4 and 5 is quite straightforward, except the superpositions of a linear system. We got to do slightly a bit, but let's go to the tutorial portion, right? Let me go to the share and then look at the tutorial question. Okay, let me stop sharing first. So it's tutorial question 4 and 5 and 6, right? So basically, if we look at the tutorial question right now, let me share again. Now, question 4 and 5, and then of course 6 here, right? So basically, 4, 5, 6, is it? 4, 5, and 8. Sorry, not 4, 5, 6. So this week we are talking about 4, 5, and 8. 8 is this guy here. 8 is this guy here. It's a superposition theorem which we just learned, right? So basically, let's go and look at 4 first. Maybe I should blow it up a little bit more. Now, what is the question state? What is the order and the type, right? Order and the type of the transfer function below. Now, of course, when we talk about order and type, we always look at the denominator. So for this case, the denominator is this case, right? S plus 2 multiplied by S plus 7, right? So denominator S plus 2 multiplied by S plus 7, if you multiply out, the maximum power for S will be S squared. So the order is definitely, for S squared, is S to the power of 2. So the order is second order, right? So the order, needless to say, is quite straightforward. But as for the type, later I will try to illustrate it, going through all the orders first. Okay, let's look at this. The part B. What is the order? The order, if you multiply all of them together, the highest power will be S cubed. So the order will be S to the power of 3, and therefore is the third order solution, right? Third order, quite straightforward. Now this is again S times S, highest power, is a second order S squared. So the order is second order, right? Now this case, there's no multiplication involved. The highest S power is S to the power of 1. So it's a first order, right? Now, if we talk about the type, then, okay, let me illustrate using the whiteboard. And let me set up the whiteboard first. Give me a while to set up the whiteboard. Now, so the first question is 1 over S plus 2 and S plus 7, right? So the first equation is 1 over S plus 2, S plus 7. Now for the type, we always look at the s plus 0 term in the denominator. That means s plus 0. What is s plus 0? S plus 0 is actually essentially s, right? So when you have s to whatever power, that particular power, that particular sx, this x is a power, will be the type, right? If it is s to the power of 0, s to the power of 0 means that it is equals to 1, right? So this is type, this one will be type 0, right? Now if it is s to the power of 1, then it's 1, is s, right? Is s. So this will be type, what do you say? It's type 1. Of course, it's s squared, then it will be s to the power of 2, right? So therefore, this is type 2, so on and so forth, right? So it's actually s to the power of 0. So down here, there is another s to the power of 0. So this is type 0. Okay, because the power is 0, right? So for the second case, of course, this is for the 4a. This is for 4a. Now, how about 4b? 4b, you have s 1 over s, s plus 2, s plus 7. Now the type is belonging to this one, right? S. Now this s here, it means is s to the power of 1. So the type 1, because it's 1. If it s to the power of 0, it's type 0, right? So as simple as that. So this is 4b, right? So let me move my mouse here. So this is for 4b, right? 4a, 4b. Now what about C? C is again the same, but of course I'm only looking at the denominator. For example, just now for the 4a, the numerator is actually ks plus 2. So maybe I should write it down as ks plus 2, s plus 2, s plus 7 or 2, s plus 1. So this is for 4a. Now for 4c is actually the same denominator, but it's 1 over. There is no, it's k over s plus 2, s plus 7. So this case, again, it is, there is s to the power of 0 here, right? Again, it is type 0, right? 4c. And 4d, again, 4d, it is the first order system type is RCS, right? RCS plus 1. So RCS plus 1, it is something like bracket, right? This is RCS plus 1, and there is no s here. So basically, it's s to the power of 0 here again. So it's type. We found it as 0, 1. This is type 0. I have not right here. Type 0, 0, 1, 0, 0. Right. So if we go back to the question again, you realize that it is type 0, 1, 0, 0. So it's the same as what I have mentioned, right? So this is to teach you how to look at the system type and order, right? Now for the second part, which is question 5, it asks you to determine the process gain, time constant, and settling time for the following transfer function. Now this is basically a first order transfer function, right? Basically a transfer function. In order to find the settling time and basically the process gain and time constant, basically we need to do what? What do we need to do? We need to compare to the generic equation, isn't it so? We need to compare to the generic equation, right? So let's do it in the whiteboard again. Let me share the whiteboard. I hope you can copy down this, or you have screenshot. Let me clear all. If not, you can replay the video again. Okay, so now let's go on and basically try to solve for the first equation, which is phi number 1. Phi number 1 is g over 2 over 0.2 s plus 0.5. G of s equals to 2 over 0.2s plus by 0.5, right? Now this is basically the first order equation. Now first order equation, what is the generic transfer function? Remember, it is k tau s plus 1, right? So this is your generic equation. Now if I want to compare these two, can it be compared? Because this side here is not 1 and this is 1, right? So it cannot be equal. Or can you see? It cannot be equal. Just for the denominator itself, it does not reconcile, right? Because 1 and 0.5 can never be equal. So what we need to do at first, we have to make sure that this is 1. So in order to make sure that this is 1, I got to divide by itself. So 0.5 divided by 0.5, it give you 1. So if I divide this term by 0.5, then every other term I have to divide by 0.5. So basically on top you get 2 divided by 0.5, right? 2 divided by 0.5, and bottom you get 0.2 divided by 0.5, right? S plus by 0.5 divided by 0.5. So basically this will give you your 0.2 divided by 0.5. What do you get? It should be 0.2, sorry, 2 divided by 0.5, you get 4, right? So basically you have 4 on top. Then of course this you have 0.4 over here, 0.4s plus by 1, right? Sorry, this is 0.25, no, 0.2, yeah, 0.2s. So it's 0.2 divided by 0.5 is, right, here 0.5 is 0.4, right? So basically if you look at here right now, it is more comparable, right? So this guy is 1 and that guy is 1, right? So now with this, we can say that what is k? K, the gain, steady state gain k is 4, right? And what is tau? Tau is 0.4, right? Just by comparing each of the term, tau is 0.4, 0.4. So, and then what is your settling time? This settling time is actually 5 tau, which is 5 times by 0.4. You get what? 1.6, right? 0.4 times 5, you get 1. Sorry, it's 2. So you get 2 seconds. So these are the 3 solutions for your first question, right? First question. Oh, so this is your first question for question 5.1, 5 part 1. So this is 5 part 1, right? Now what about 5 part 2? 5 part 2 is slightly different only. Is g of s is equals to basically 0.2 over again 0.05 plus s plus 0.1, right? S plus 0.1. So basically it's just like that. So basically again you need to compare to this and you need to make this guy equals to 1. So we repeat the same old thing. We just divide 0.2 divided by 0.1 on top, and 0.05 we divide by 0.1 s plus by 0.1 divided by 0.1. So 0.2 divided by 0.1 you get 2 over this one you divide by 0.1 you get 0.5 s and plus by 1, right? So basically right now here your what is your k? K is 2, right? For this case k is 2 and tau will be 0.5 and settling time is ts is equals to 5 tau, which is 5 times 0.5, which I think is 2.5 seconds, right? 2.5 seconds. So these are the 3, or rather these are the solution for 5 part 2. 5 part 2, right? So now let's take a look at what we have solved. Is it correct? So let me go to what we have just did. So you can see it's 2.5 and 2.5, and this is 4.4 and 2. So basically we have nailed this question. Now the last one that we're going to do is page question 8, right? Question 8. Now question 8 deals with, again, is superposition. Okay, let me scroll down a little bit. So if you recall just now what I covered in the lecture, we say that, hey, the output is affected because this is a linear system. Linear system means that and then it obey the superposition theorem. So that means that you have two input but one output, right? So if you have, you can consider the effect of one input and then zero down the one of the other input and then look at the y prime. And the next moment you do for the other input and you call it y prime prime, and then you add both of them together to get the final value result. So basically, we can try to solve this using a whiteboard. So first of all, I will clear the drawing. You have a page and that portion, right? So basically, for let's draw up the system first. Let's draw up the system for is k over s plus 3, right? S plus 3. That is one of the gain, and then the other one is 2 over s, and then of course the feedback is s plus 1. So these are your three blocks that is involved, right? The other box is here, and of course there is a summing point at the middle. Summing point at the middle. Right, summing point at the middle, and of course there is another summing point in front. And this is a negative summing point here. And of course the output is fed back. Output is fed back, and this is what we term as ys. And the other one is rs and ds. So ds is the disturbance, and rs is your reference input, right? So now, of course, we got to first define. Yeah? Let's say, for example, in the first situation, we set d of s equals to 0, right? Then we consider the effect due to rs, right? R of s causing what? Causing the output, say we call it y prime of s. So we look at the effect first in this sense. So if we look at it in that way, so if I remove the effect of d of s, so likewise this summing point become useless. So I can remove this summing point at the same time, right? So if I remove this summing point at the same time, then now I can fully concentrate on the effect of r of s to y of s, but now it should be called y prime of s, right? So now what is the forward side? What is the forward side? So forward gain is actually basically this multiplied by that, right? So it's actually 2k, right? Is 2 on top, 2 multiplied by k is 2k, and bottom is s plus 3, right? s plus 3, green, right? I hope I never copy it wrongly. I just double check at the back. Oh yeah, it's correct. So basically, if this is the case, I just combine these two blocks, it becomes like that. So basically, I can erase away this guy. I combine these two blocks, and it becomes 2k over ss plus 3. Right, so this is your block now, your new block now. Now again, this is a negative feedback. This is your G, and this is your H. Now you can basically do a what? Do a rule 7 simplification. G over 1 plus GH. So your G is basically 2k over s plus 3, right? S plus 3 over what? Over 1 plus 2k over s plus 3 multiplied by your s plus 1, right? Is it s plus 1? Yeah, it's s plus 1. So if you multiply that up, what you get is actually same thing here, 2k over s plus 3 on the top. Then of course this 1 here you use the same denominator, so it's s plus 3 over s plus 3. Now this is equivalent to 1, same thing, because the same thing divided by itself is, and why I choose the denominator as the same denominator for all is because of the reason that I want to sum the denominator up, right? So here you multiply in is 2k multiplied by s plus 1 over s plus 3. So right now you see that all the denominator is the same. So basically, the next step is you can actually, rightfully, you can just cancel out all the denominator here. Right? You can just cancel out all the denominator here. Let's say I do a cancelling of all the denominator, right? And then what I can do is I just write out all the numerator. So the numerator will be 2k for the top, right? Because there is no more denominator. Then this one will be s plus 3, s plus 3 plus by 2k s plus 1. So basically, that is your expression. So y prime, y prime. So if I write at the corner here, y prime s is actually equals to 2k over s plus 3, s plus 3, and plus by, this is s plus 3, yeah, and plus by 2k s plus 1 multiplied by r of s. So this is your y prime. So we just determine one of them right now. So right now, if I erase away the whole thing and I do the second portion, do the second one, which is do the second part due to your d of s, right? Due to the d of s, and let's see what is the effect. So we keep the result of due to the r of s, we keep this result, and then now we proceed back to the same circuit and do it for the d of s. Right, so again, k over s plus 3, 2 over s. So redrawing is k over s plus 3. And then the other one is 2 over s. You got 2 over s here. And of course, below is s plus 1, right? So your 3 blocks are here. Now, of course, this is your summing block, which plus here. You got sum here. Then is your d of s here, right? And then you have the feedback. There's another summing block here, plus, minus, go here and here. So your r of s is actually here. This is a plus, and then your c of s, right? A y of s, not c of s. So it's a y of s here. Now we want to look at the effect of y of s due to d of s, and without the presence of r of s. So basically, first step, we delete away r of s, right? We delete away r of s, and we rename this guy that is, we call it y prime prime, which is due to d of s. Now, if I want to remove this guy because of the negative sign, I got to insert a minus sign here. So basically, what I can do is I put it as red color. I put a minus sign here. I bracket it minus sign. So then I can straight away remove this guy. I can remove this guy and just connect it up, right? So this is the minus sign is taken care of. Right? So this is connected. So let me put it back to black, not all to black. So basically, it's like that. Now this again look like the positive feedback, right? So this is the forward portion. This here to here is the forward from input to output. But the feedback is all the way from the y back to your d. Yeah? So basically, oh, oops, I deleted accidentally the box. So basically, feedback is from here back to here, back to the d. So basically, we can combine this feedback portion, right? So you can combine it as what? Basically minus k. So it's basically minus k over s plus 3, right? Sorry, k over s plus 3. This is plus k, no minus k. Plus k over s plus 3. But then because there is a minus sign, you got to minus multiply by s plus 1, which is a minus sign here. So this become minus because of this minus sign. Also, if I rewrite, then this whole thing can form a block, right? This whole thing can form a block of the feedback path. And then, of course, I can redraw this guy here as minus k s plus 1 over S plus 3, right? And then of course this is your feedback, right? This is your feedback here. Of course, if you like, you can redraw this guy here. Instead of pointing here, you put it at this direction, T of S, right? So it looks more like a positive feedback expression, right? It looks more like a positive feedback loop, right? Now, with this positive feedback loop, now you need to resolve this whole thing as G. This is your G and this is your H, right? Now, so it's G over G. G is 2 over S over 1. Because it's a positive feedback, is a minus, right? Plus become minus. And then, of course, your G. G is again 2 over S. H is this guy. H is slightly complicated. It's minus K S plus 1 over S plus 3, right? So if you try to solve this, you got 2 over S. Sorry, maybe I got to write properly. My handwriting is not very nice. Okay, so then you have 1 minus. Minus and minus become plus, right? So it's a plus here. And you can 2 multiplied by K multiplied by S. So it's 2K S plus 1, right? Over S times S plus 3 is S plus 3. Now, the top and bottom right now has a problem because you don't have the same denominator. So what I want to make is, basically I want to make the top and bottom also the same denominator so that later it's easy for manipulation. So what is different for the top and bottom is S plus 3. So if I insert the S plus 3 here, I got to insert the S plus 3 on top, right? So that they are balanced. You can cancel it out, it's still 2 over S, right? So now top and bottom have the same denominator. Now likewise, this guy don't have the same denominator. I will make it into S plus 3 over S plus 3. So this is equivalent because S over S plus 3 divided by itself is 1. So now you got 3 of them, all the same denominator. So what you can do is you just basically cancel out all the denominator, right? Cancel all the denominator and then write out the numerator. Write out the numerator. Now what is the numerator here? On top is 2S plus 3, right? On top is 2S plus 3. Over the bottom is S plus 3, right? Plus by 2K S plus 1, right? So basically you have just solved the expression. So now you can, of course, replace this guy, the whole thing, by the new expression, right? By the new block, right? So basically you can rewrite this guy as a 2 over S, 2S plus 3 over SS plus 3, SS plus 3 plus by 2K S plus 1. So this is your new expression. So your y prime prime, S is actually 2S plus 3 over S plus 3, S plus 3 plus by 2KS plus 1. Multiply now is by D of S. Right, D of S. So basically your Y is actually, Y of S is actually Y prime of S plus by Y prime prime of S. Each one due to the respective one. Now you notice that this denominator, both of them are the same. So basically you can rewrite the numerator, right? Numerator is 2K times by R of S, right? So basically your is 2K RS, 2K R of S. And this guy, the numerator is plus by 2S plus 3 D of S, because this is the numerator. Then I combine the denominator, right? I combine the denominator. Denominator is, again, is S plus 3 plus by 2K S plus 1. So this is your final expression. how your Y is due to your R of S and D of S. Now, if you compare the result of this guy to the result that is in your solution, let's take a look at, do we get the solution correct? And basically, I think that's it. We got it. 2KRS, right? 2KRS, 2, yeah. So basically, it has a 2 in front. It's more or less there, right? Yeah, 2KRS. So it's basically the same. So with that, we finish the tutorial discussion and the lecture for today. And I will stop the sharing now. And of course, I wish you all the best. I will end here. Okay, thank you and have a good day.